Okay, so let's start. So today it's our honor to have Professor Willie Wong from Michigan State University. Professor Wong's research focuses on the interaction of geometry and partial differential equations, for example, general relativity. So today, the topic of his talk today is about blowing hot air at Big Bang. Let's welcome the speaker.
Thank you. I'd like to just begin by thanking the organizer and Professor Wu for the generous invitation to speak at Tsinghua. So the subject of my talk is going to be on mathematical general relativity, and it is a subject that has seen some resurgence in recent years with quite a few major results being proven. And this is primarily in the hyperbolic setting where you look at the evolution equations, which is sort of in contrast of the golden age of relativity in the 80s, where a lot of the results are in the elliptic direction. So today I'm going to talk about some things about Big Bang solutions, and understanding that many of you are master's students, I'm not going to assume very much in the background. I'm hoping to give you a bit of a flavor of what this kind of research is all about. Okay, so we're going to start with prologue, which is going to tell you a little bit about mathematical GR and what the problem that we're trying to study is for this particular presentation. The motivating question for me is the following: whether the cosmological Big Bang solutions are reliable representatives for studying the early universe. I'll explain a little bit more what this sentence means. In particular, in this prologue, I'll talk about what the model is. So in this case, this will be the general relativity. I'm going to talk about what cosmological Big Bang solutions are, okay, and why we actually are thinking about them. And finally, there's this mysterious phrase, whether they are reliable representatives. So I'm going to explain what it means for a solution to be a reliable representative. All right, so very quickly, this is a one single slide explanation of general relativity. Okay, so in general relativity, we're going to be studying, this is it's a theory of physics, and this tells us how things evolve on space-time. And so I'm going to present to you first the actors in this discussion, and also the rules for how they evolve. So firstly, space-time is an unknown in relativity. So the domain in which you solve all your equations is itself part of the unknown. It's going to be a smooth manifold M. And this is one of the big differences between relativity theory and many other geometric PDEs, where you start out with a manifold that's given to you and then you solve the geometry on there. Here we construct the manifold as we go along. Now, general relativity is a theory of gravity. And so gravity, many of us should be familiar with the Newtonian notion of gravitational physics. And we understand that in the Newton's point of view, the gravity is given by a gravitational field. And this is related to the matter mass density via Poisson's equation. Okay? And so in Einstein's general relativity, the gravitational field is replaced by the Levi-Civita connection of a Lorentzian metric G on M. Now, if you have not done in geometry, this sentence doesn't mean anything to you, but if you've done some geometry, then you have some idea that the connection is something that lives at a level of the first derivative of the metric. So you should think about if the connection is the gravitational field, then the metric itself should play the role of something like the gravitational potential. Okay. Aside from gravity, there's also going to be matter in my universe. So the matter content of the universe are going to be some geometric objects over M. And I'm not going to specify what they are. They can be scalar fields, they can be tensor fields, they can even be something fancy like a section of some fiber bundle. But important part is that we want them to be geometric. We want them to be something that can be described invariantly using geometric data. And this is because of one of Einstein's key insights, which is the principle of general covariance. And it says that essentially the laws of physics should be independent of frame of reference. And because of that, you should actually only study physical objects which are independent of parameterization, independent of coordinate choice, and these are natural geometric objects. Now, so we have introduced what our things are. We have the gravity, we have matter, we have the space-time. We need to talk about how they evolve. So first, we talk about how gravity factors into the matter equations of motion. So when matter evolves, we have to sort of factor in how gravity influences how bend their trajectory. And this we're going to rely on Einstein's equivalence principle, which basically says that if you have a physical theory with no gravity, which is expressible as a partial differential equation, then in the gravitational case, you just need to go in and replace every single partial derivative with a covariant derivative. Okay, that's sort of the easy way of understanding what's going on. And that tells us exactly how matter should behave under the influence of gravity. On the flip side, we also need to talk about how gravity is generated by matter. And this is Einstein's equation. And this tells us how G, how the metric, and by extension, how the connection change in response to matter in the universe. And together, the evolution equations are given by two parts. There is a matter equation of motion, and there's Einstein's equation, and together they form a system of nonlinear PDEs. Okay? Yeah, does it have a pointer? Oh, it does. All right. So having talked about the equation, the model, the sort of problem that we're interested in solving is the initial value problem, right? Basically, the question of if we know what's happening right now everywhere in the universe at this very moment, can we use this to predict what's happening later at a different time in the universe? And so the data we're going to prescribe is an initial time snapshot of the universe, and it's going to be given by space, which is a given smooth manifold, sigma, with one fewer dimensions than the space-time. Now, space-time is one-dimensional. Okay. So since the data for, since the space-time itself is part of the unknown, space, the spatial topology, has to be prescribed also as an initial data. We also need to give conditions for the gravity, which, recall, is modeled by a metric. So since we're looking at something that's sort of physical, we have a second order differential equation, and therefore we need to prescribe both the initial position, initial velocity for the metric. And this takes the form of a Riemannian metric on sigma, and then some 2 tensor, which is actually the second fundamental form of sigma. And finally, we're also going to prescribe some initial conditions for matter. So this will be values of the geometric objects, maybe its first derivatives over the spatial manifold sigma. So given this kind of prescription, a very sort of well-known result from 1952, Shekoi-Bruhat, and then the 60s, Shekoi-Bruhat and Garrosh, proves the local well-postedness of the initial value problem. And it says that for reasonable matter content, and don't worry about too much, but this just means that the things that we can prove the theorem for reasonable matter content, given sufficiently regular initial data, so here you should think something like C20, 20-time differentiable, then there exists a unique maximal solution to the initial value problem. And I'm going to come back to this unique and maximal notion a little bit later, right? So the idea is that here the statement is a lot like the Picard-Lindelöf theorem for ordinary differential equations, that we can solve the solution, we can solve the equation given the data, we can solve it as much as we can, a maximal solution, and this maximum solution is going to be unique. Okay. This will be a little bit of an issue a little bit later on, but I'll defer that to when we talk about technical parts of the argument. All right, so that tells us what the model is. Next, let's talk about what are the cosmological Big Bang solutions. So what is the word cosmological in this context? The cosmological ansatz is an ansatz that people use to study cosmology. Cosmology is the sort of overall evolution of the universe. And the ansatz proposed, depending on what you study, they're usually more than just this particular assumption. But I'm just going to assume on a very minimum level that we have what we call spatial homogeneity. Okay? And what does that mean? That means that our space-time has a cosmological time function. You think that there's a clock ticking sort of way out there somewhere that tells us exactly what time it is from the point of view of maybe a god or a ambient observer. And we're going to so we have an agreement on what the current time is on the space-time, and we're going to assume that if you have 2 points with the same time, so if the time at 2 events are the same, then there must exist some isometry from your space-time to itself that brings the 2 points to each other. Okay? So this means that we cannot distinguish two individual locations apart at the same time. And to go along with that, we're going to require that our matter model also is invariant under the transformation. So if I go from one point to another point via this isometry, then the matter that you observe at one point is going to look exactly like the matter you observe at the other point. Okay, so this is spatial homogeneity. So once you impose these conditions, then you can see that there is no dependence on space anymore. And therefore, there's only time dependence, only depends on tau, the cosmological time function. And so the equation of motion immediately goes from a system of highly coupled, highly nonlinear PDEs down to a system of ODEs, and it's finite dimensional. So why do we use this ansatz? Well, so there's two parts of this. There's the physics part, and this is a hypothesis. This is not something that is, testable even on an experimental level. It says that on large scales, if you sort of back away from the universes, from everything else, from the galaxies and from the stars, on large scales, your matter is well approximated by a homogeneous fluid. Okay, that's just an assumption. That's an assumption by physicists who says, hey, we're just going to look around and say and pretend that we are not in any way special. That what we see here is pretty much the same as what we see anywhere else in the universe. Okay, so this is just a hypothesis, and this is a hypothesis that will be the sort of the discussion of this talk. On a practical case also, though, we look at cosmological ansatz because PDEs are a lot harder to solve than ODEs. So once you reduce everything to ODEs, you can try to analyze the ODE and try to find out a qualitative behavior of the solutions, and we can then hope that these things that we discover for the ODEs can be used to inform our understanding of the full PDEs. Okay. All right, so that's what cosmology is about. Now, what are the Big Bang solutions? So once you assume the cosmological ansatz, that everything depends on time, then the manifold space-time is going to be something like an interval of time cross the spatial cross-section sigma. Okay? And the metric is going to take the form minus alpha t squared d tau squared times some spatial metric which depends on cosmological time. Okay. All right. In particular, this metric is homogeneous. So sigma under this is a homogeneous space. It does not depend on where the metric is independent of where you are on the spatial slice. Now you can ask, okay, so I can always sort of reparameterize taus to make alpha equal to 1. Why do I keep this alpha here? This is because sort of for some discussion later on, there are actually geometric taus that we can consider which have non-trivial coefficient in front. This is just sort of a convenient to allow myself to have other normalizations than the obvious one. Okay, so what does it mean for a solution to be a Big Bang solution? Well, Big Bang is the thing that happens in the beginning of the universe. It's singular, so we're going to require some curvature, the curvature of my space-time to blow up at the initial time, tau 0. And sort of our intuitive idea of what a Big Bang is requires that everything collapse down to a very small scale. We're not going to require that isotropically. We're not going to assume isotropy. We're just going to assume that this collapse happened at least in one direction. So there's one direction in sigma such that the direction collapses as you go towards tau 0. Okay. And finally, we're going to assume that the Big Bang is finite time away. So this is sort of in accordance with what we usually expect from our current observational data for the universe, that we have something like a 14 billion year old universe. So we have we're going to assume that tau 0 is actually finite time away from our current instant in the universe. Okay, so these are what we call a cosmological Big Bang solution. Now, so the general philosophy for PDEs, as I mentioned earlier, is that we try to we're trying to find out something about the PDE, about solutions in general. But for nonlinear PDEs, this is very, very difficult. In general, you cannot say a general statement that is true for every single solution of a PDE, even on the qualitative level. We're not talking about quantitative, we're not talking about numbers, we're talking about just sort of qualitatively, the asymptotic behavior can vary wildly from solution to solution. So because of that, we look for special solutions, and special solutions which we can analyze. And for example, these ODE solutions. And we ask then, are those things that we see from this ODE solution generic? Are they actually something that we can use as basis for understanding what's going on in the world? Now, this is still a very hard question because, again, genericity would imply, so you know something about a large class of initial data. We're going to talk about something that's much more modest, which is the first step. Is the behavior under initial data perturbations stable? What does that mean? So we start out with this homogeneity assumption on the Big Bang. We're going to ask, if I take an instantaneous snapshot of the Big Bang solution, I'm just going to poke it a little bit, make it a little bit different from homogeneity. Is it true that the corresponding PDE solution, after you do that, behave exactly like the ODE solution? Okay. Of course, exactly like is something I have to define a bit. But that is a question we want to talk about. Can we use the ODE solutions as good approximations, maybe not of every single PDE solution, but of some PDE solution that are nearby this particular ODE solution? And there are some cases where there's some successes and failures of this statement. For example, in the first three I listed here are all in the context of general relativity. So Minkowski space is a very special solution to the Einstein's equation. It says that nothing is happening, there's no matter in the universe, everything is empty, everything is static. That has been proven to be stable. So if you put in only a little bit of matter, a little bit of gravitational energy, then the behavior is going to be in the large asymptotically exactly the same as Minkowski space. And this was theorem proven in '93. Stability of Kerr black holes, so you do a black hole solution, you do something similar, you perturb it a little bit, see what happens. This is a long established conjecture, and there has some work which turned part of it into a theorem, but part of it is still conjecture. I'm not going to go into details of the current status of this particular statement here. And then there is the so-called cosmic censorship conjectures, which is actually a statement that conjectures that certain type of behavior is unstable. That in the study of Einstein's equations, people have been able to write down certain solutions which look very, very pathological. And the cosmic censorship conjecture basically says that these pathological solutions have to be unstable because we don't want to see them from our idea of how the universe should look like. We want to pretend they don't exist. Okay, so the cosmic censorship basically just says that those pathological solutions are unstable. They're not something that's observable because generically they don't happen. And finally, I'm going to mention something that is not in the relativity thing because this ties into the second part of my talk, which is that there is a statement about the instability of stationary compressible fluid. So what does this mean? Now we start, the statement here is saying that if you have compressible fluid, so you think about air, okay, and you said you should start out with initial data which is entirely still, so the air is not moving. There's no wind in the in this room. Then there will be no wind later on. Okay, the air will remain motionless. But if you put in just a little bit, just blow on the air a tiny little bit, the Euler equations for compressible fluid actually predict that if you wait long enough, there will be a shock wave coming out of this. So the stationary solutions where nothing is happening is very unstable. It's unstable due to the formation of shock waves developed from very tiny initial perturbations. Okay, so all right. So that's that's about the cosmological Big Bang solutions. And now we're going to talk a little bit about stability, right? I've been using this word a lot so far, that stability. We defined earlier, I defined at least, the cosmological Big Bang using three conditions. I assume that there's singularity, there's curvature singularity initial time, there's spatial collapse, there's a collapse of some spatial direction, and that the singularity is reachable in finite time. Okay? Now the first and last are sort of well defined even outside of the cosmological onset. If I have a random solution to Einstein's equation, I can ask, on the boundary of the solution, is there a singularity for the curvature? Is the boundary reachable in finite time? But the spatial collapse requires choosing a space-time decomposition. And this one is in general dependent on your choice of coordinates. Okay, so if you want to prove dynamical stability of a Big Bang solution, this is actually something that's very, very difficult. You need to actually provide an appropriate definition of what it means to have a Big Bang outside of the cosmological setting. Okay, I do not provide this in this particular talk, nor in my result, because we're going to prove instability and not stability. Okay, so just sort of to emphasize a little bit about the idea of how singularity and stability depends on your definition of what it means to be stable, what it means to be a singularity, what it means to be a Big Bang. Let's talk a little bit about one very simple example. So a very well-known theorem by Stephen Hawking and Roger Penrose, sort of their combined efforts, is the Hawking-Penrose incompleteness theorems, sometimes called the singularity theorems, but nowadays we like to call them incompleteness theorems for various reasons. And basically, what they say is the following, that there is certain open condition on initial data. I'm not going to tell you what they are, but just believe me that these are open conditions so that they are stable under perturbations. That leads to the statement that the unique maximum solution, which is guaranteed to exist by Schoenberg and Garrosh, this is geodesically incomplete. Okay, this is sort of their statement. So if we use geodesic incompleteness as a definition of space-time being singular, then Hawking-Penrose theorem tells us, hey, we have stability automatically because the hypothesis is open. However, if you dig a little bit deeper and look at how a manifold can become geodesically incomplete, there's going to be three different ways for this to happen in relativity. First, it's kind of weird part, is that there's a possibility of you running into what is called a Cauchy horizon. What this means is that the geodesic will want to exit your space-time without hitting any singularity. And you ask yourself, wait a second, how can this happen? I'm talking about unique maximum solution. This solution is maximal. How can I leave the space-time when I have a maximum solution? Well, the issue here is because, going back, a problem or a feature or relativity is that the space-time itself is part of the unknown to be solved. So if you take a solution to the Einstein's equation, and you take a second different solution to Einstein's equation, take the disjoint union, you get a new solution. And these two solutions agree on some parts. Okay, so because of that, there is an issue of uniqueness. In general, uniqueness need not hold for something that's so geometric, that has so much freedom in defining what the domain of the problem is. So what people do impose is an additional condition called global hyperbolicity, which allows you to restrict what kind of solutions are considered viable. And once you impose that, this gives you a condition on what the size of the maximum solution there is. And that gives you a possibility for you to run out of the space-time, because the space-time just somehow ends with no sort of indication that it's going to end. So that's a sort of one of the sort of pathological pathologies that you see in GR. And actually, I'm talking about down here that strong cosmic censorship, Wong conjectures, precisely states that Cauchy horizon should be perturbed away into curvature singularities, that this should be unstable. Okay, but these are known to exist. There are also sort of more natural versions of geodesic incompleteness where the geodesic terminate at a singularity, either from the geometric singularity, something that comes from the gravity part of this universe, or something coming from the matter part of the universe. Okay. So my contention is that if you have a perturbation that changes the types, so you start out with a solution that has, say, curvature singularity, and you perturb it a little bit, and you end up with, say, a matter singularity. My idea is that this should be considered as something unstable, because you're changing how singularity is formed. Okay. And so if you accept this, then the Hawking-Penrose theorem does not tell you anything about stability of the spacetimes. Okay, so now I'm ready to sort of state a very quick preview of the main result, which is that we prove, so this is my student Shifang Ye and myself, we proved that a class of cosmological Big Bang solutions in the Einstein-Euler model of self-gravitating compressible fluids, this class is dynamically unstable. In fact, there exist arbitrarily small initial data perturbations that turns the curvature singularity of the Big Bang solution into a matter singularity. Okay. All right. So now, with the prelude out of the way, let's go in slightly more into the technical part. I'm going to first introduce the Einstein-Euler model, and I'm going to talk about the warp product symmetry that we'll be using. So the Einstein-Euler system models a fluid that's evolving under the influence of gravity. Okay, so the unknowns now we have, as before, we have the metric G, the manifold M, which is implicit. We have a fluid density, the density of the fluid itself, and the velocity of the fluid. The equation of motion is going to come in these 5 equations. The first one is Einstein's equation, which tells you how gravity is generated by the matter. Euler equation has 3 parts. First part is a physicality restriction. This is saying that sort of in physics, we like in relativistic physics, we like the forward velocity of a particle to be given by a unit vector. So this is just what it says, a normalization. On top of that, we need to have conservation of mass and conservation of momentum. So that's Euler's equation. And then we have this final equation, the equation of state, which says P equal to P of rho. Notice that P is not one of the things up here. So what is P? P is the pressure. The pressure is not an unknown. It is given as a function of the pressure. And given a function of, not a pressure, this is a given function of, mistake here, this should be a function of the density rho. Okay? The idea is that the pressure models how your fluid responds to being compressed, right? If you take air, you compress it down, you get higher pressure. And if you take the same blob of air, you let it up again, the pressure decreases. That is what we're trying to do here. We're saying that the pressure actually depends on the density of the fluid. Now we're going to ignore fluid entropy, otherwise P will depend on the entropy also, but this is sort of a technical assumption we're going to just not talk about. So to make the equation, so to make the model complete, we had to prescribe an equation of state, which is a function P depending on rho. We're going to choose a particular function P. This P, we're going to choose P equal to a linear function of rho, P equal to gamma times rho, with gamma belonging to 0, 1. This is called the ultra-relativistic equation of state, and it is a common equation of state used for astrophysical studies. Sort of, basically, it says that sort of the underlying assumption is that our everyday experience of fluids, where we have very complicated equation of states, this all happen for very slow velocity, very small amount of compression. Once you get a higher amount of compression, then things become sort of linear. Okay. Gamma turns out to be local sound speed relative to fluid motion. Okay. Gamma equal to 0 is so-called a dust model. It's a special case. It's one of the endpoints. In this case, the fluid particles don't interact. Right? Pressure is always equal to 0. So there's no response of the fluid to being compressed. So this is a case where the particles don't interact. There's no restorative force pushing the particles apart. Gamma equals to 1 is an interesting case. Gamma equals to 1 is called a stiff fluid, and it's actually equivalent to a linear scalar field. So in general, the equation of fluids is a nonlinear particle differential equation. But when the gamma is equal to 1, it mysteriously linearizes itself. Okay? And this is one of the reasonable models, so that Shoukei, Prof, and Garage proved a locally well post. Okay. So, yes?
Is gamma fixed or depends on position?
Sorry, the gamma? Oh, gamma is fixed. Gamma is a fixed constant, yes. When gamma depends on, well, gamma should not depend on position because gamma is sort of a thermodynamic law. So it should be uniform in the universe. Now, but gamma, but the form, the linear assumption, of course, can be changed to a nonlinear assumption. So P may be a nonlinear function of rho. And what my expectation is that our results should also work in those cases, but the proof will be a lot more complicated, just for technical reasons. Okay. So it turns out in recently, actually, this is in the past about 10, 15 years or so, there have been some work demonstrating the opposite of what I'm talking about. People have proven the stability of cosmological Big Bang solutions in some cases. And in those previous cases, they only work with Einstein vacuum, so there's no matter, or the Einstein scalar field model, which is the gamma equal to 1 case. Okay. And the idea is that they're only looking at whether gravity itself is stable. What we're trying to do is we're trying to study the impact of the nonlinear matter model on the stability of Big Bang. Okay. And this is sort of interesting because in the absence of gravity, as I talked about earlier, compressible fluid generally becomes singular from shock formation. This is the instability of stationary compressible fluids. And this actually goes back to Riemann. It's the first example of this result. And there's also a bunch of work in 1950s and 60s on this idea. And more strikingly, though, there's previous work by Rendell and Stahl. And they showed that shock-forming solutions of Einstein's Euler equations are possible. But in their case, they have to start from well-selected initial data. And they are going to work in a case where it's very far from spatial homogeneity. Okay. So in particular, they're going to choose fluid components being sort of dominating the gravitational effect. So basically what they're doing is that they are putting in initial data where a shock is almost going to form and then prove that, yes, it does form. Okay. Our goal is to try to prove something that perturbs from spatial homogeneity, that in near spatial homogeneity, we can still have this nonlinear feedback that generates shock waves from very small perturbations. Okay, so our setting, as I said before, is that basically would shock formation still kick in from the nonlinear matter model when the gravitational effects initially when the gravitational is dominated by this is correct. When would the shock formation still kick in when the gravitational effects are large compared to the fluid effect initially? Okay, so we're going to be imposing what we call a warped ansatz in this particular result. And this is following and generalizing the result of Rendell-Stahl. Basically, the idea is that we want to reduce our PDEs to a 1 plus 1 dimensional PDE instead of a 1 plus 3 dimensional PDE. And the reason for this is because, firstly, proving shock formation is a lot harder in higher dimensions. And there's a overview article, that I wrote with Kleinerman, Hotzeko, and Speck that so details why exactly shock formation is very hard to prove in dimensions bigger than 1. And also, it turns out geometry is a lot easier in the warp ansatz, and this is some analysis I did with Anxin Liang at Singapore. So what we're going to do is we're going to assume that our manifold factors into a 2-dimensional base manifold with some fiber on top of it. Okay, and the metric is going to also factor into a Lorentzian metric with a word product with some Riemannian metric GF. And the R is called the warping function. It basically tells you that how big the fiber is. So you should imagine, so the picture you have in your head is that you have a 2-dimensional base manifold and little sort of higher dimensional hair growing out of it. And the R measures how big this hair is at every single point. Oh, wrong part. There we go. Okay, so one of the interesting things is that this assumption here is only an assumption on the form of the metric. This is not saying anything about the matter model. One of the results that I proved with Xin Liang is that if the underlying space and factors, then everything becomes homogeneous in the fiber direction. So firstly, the fibers must be Einstein manifolds. The density has to be constant on fibers, and the velocity has to be tangent to the base manifold and independent of the fiber. Okay, and in this case, we can also reduce the Euler equation, Einstein's equation, but then let's not look at these words. Let's just go down to the next slide. So in our setting, we're going to assume we're trying to study whether spatial homogeneous solutions are stable. So we're going to start with a solution that's spatially homogeneous. Spatial homogeneity then will require this warping function R to be a spatially homogeneous function. And therefore, we can actually choose by cosmological time as precisely the warping function. Okay. Because the base dimension is 2-dimensional, and this is the part where we have some interesting, some basic geometric computation we can use, we can select an orthogonal coordinate system and use S to denote the complementary spatial coordinate. So we have R, which is the time variable, and S is a space variable. And now we can reduce everything down to the following system. We have some parameters: the scalar curvature of the fiber, the dimension of the fiber, the gamma, the constant, and the cosmological constant lambda. We have unknowns, the metric. Since it's diagonal, there's only 2 components of the metric. We have the density, and we have the velocity. Now, the velocity is effectively scalar because we're requiring it to be a unit vector A unit vector in 2 dimensions only has 1 degree of freedom. Okay. So the Euler equation now becomes a hyperbolic system for rho and c in with variable coefficients and with weights actually. And then the Einstein's equation, interestingly, this is a part that's kind of neat, is that when you have so much symmetry imposed, Einstein equation simplifies drastically. It becomes a system of transport equations for the metric components, and it's elliptic hyperbolic type. So we have 2 evolution equations plus 1 constraint equation. And if you have done any sort of GR before, constraint equations is one of the things that you have to live with in Einstein's equations. And it turns out that this actually is good for us, having the constraint. Okay. So now we have to introduce very quickly the model. Let's talk a little bit about what are the Big Bang solutions now, because I want to talk about what they are and before I start perturbing them. So with the warped ansatz, as I said before, we have fiber homogeneity automatically. So to impose spatial homogeneity, we just need to make sure that everything is homogeneous on Q, the base manifold. So this is equivalent to there existing some Killing vector field on Q, which leaves the metric invariant, the density invariant, the velocity invariant, and also the R variable invariant. And the final condition actually tells us something that's interesting, because that we can now normalize my spatial coordinate system such that eta is equal to partial s. Okay, this just makes computation a lot easier. And with this, the equation of motion now reduced to a coupled system of 4 first-order ODEs for GQ, rho, and C. Remember, GQ has 2 components, it's diagonal. Rho is a scalar, and C is effectively a scalar. So it's 4 ODEs. Now, 4 ODEs are still kind of messy. It's kind of hard to analyze 4 ODEs. However, it turns out that the constraint equation does something interesting. It forces C to be parallel to the gradient of R. Okay, this is something that is not true without the gravitational coupling. This is something that's a purely gravitational effect. Okay, and so this means that the fluid velocity has to be 0 relative to spatial coordinates. So basically, this is an interesting effect where if you're looking at the non-gravitational fluid, you can have all the fluid moving in one direction, and that would be a stationary solution to the Euler equation. But once you add gravity, that is no longer possible. For a stationary solution, the fluid has to stay still. The conservation of mass and energy also provide one more conserved quantity. So now we have 2 conserved quantities, which reduce the equation of motion down to a 2D dynamical system, which is great because once you have a 2D dynamical system, you have no chaos. And you can also rule out some very complicated settings, such as the BKL conjecture. So the Bianchi-9 attractor has a symmetry that reduces everything to a 3-dimensional system. And 3-dimensional systems can have sort of homoclinic orbits, which are kind of complicated. But in 2-dimensional case, that doesn't happen from just counting indices. So we have a chance to actually completely classify all the solutions to the Big Bang the Big Bang equations. Okay, so our classification, this is what I did with my student Shifang. It says the following. Okay, so here, importantly, gamma is between 0 and 1. It turns out that gamma equal to 0 and gamma equal to 1, they have very, very different asymptotics. So, this is what I'm talking about here is only for gamma between 0 and 1. Suppose that the maximum solution defined for R0 to R infinity and Big Bang can only occur at R0. And furthermore, there are only 3 possible types of asymptotics, full classification. And here, when I take Paul these are the exponents to R minus R naught. So you should think about here when I say 2 gamma, I lost the thing. Okay, so we have 2 gamma over 1 minus gamma. This is saying that the component is going to 0 at the rate R minus R naught to the power 2 gamma over 1 minus gamma. Okay, and I want to highlight a few things. So here, this is positive power, negative power when n is bigger than or equal to 2. Okay? All right. So we have actually 3 different types of possible geometries. Remember, we're looking at a situation where we have a base manifold two-dimensional with some hair growing out of it, which is higher dimensional. And we have an R, which measures the length of this hair going out. In this particular, in the first column, what we have is that we don't have any fiber collapse, meaning that when you approach a singularity, your hair remains a finite size, finite non-zero size. Okay, R0 is bigger than 0. But we have spatial collapse in the q direction because that particular component is going to 0. Second column, you have fiber and base both collapse. So in this case, the fiber goes to 0, fiber shrinks, and the base manifold also shrinks to a single point. And the final case has the fiber collapsing down to 0, but interestingly, the base is expanding. The base is growing, it's expanding in scale unboundedly. It's going to infinity. Okay? These are three very different, and there's actually no in between. There's no case where the base actually converges to constant. Okay. So these three classes. So then this is the part where I think is something interesting in terms of comparison. So the middle case where the fiber and base both collapse, the spatial sections, the cross sections are shrinking isotropically at a rate r squared. Okay. So it turns out this is exactly the rate you have for the Freeman-Lemaitre-Robertson-Walker model in cosmology, the FLRW Big Bang. And the FLRW for Big Bang for gamma equal to 1 was proven to be dynamically stable by Roniensky and Speck. This is about 10 years ago. And then the case where the fiber collapse with base expansion is happening, okay, where the base manifold is expanding, growing unboundedly. This is actually geometrically very similar to the so-called Kastner solutions in cosmology. And the Kastner Big Bang for the gamma equal to 1 case was proven to be stable by Furneaux-Davlos, Roniensky, and Speck. And this is a very recent result, only about a year, 2 years old at this point. Okay? And so our instability result is the other case, the case where there's no fiber collapse. Okay, so we're not in any sort of contradictions with existing results here. So why is there a difference between what they did there? So of course there's one difference, which is they study gamma equal to 1 and we study gamma between 0 and 1. So we have extra nonlinearity. But I think sort of my conjecture is that is not the key reason why it's different. The key difference is because that we have very different conformal structures in these three cases. So to talk about the conformal structure, I need to talk a little bit about this notion of Penrose diagram, which is rigorously defined for spacetimes with warp product structures. Okay, and this is because once you have a base manifold Q, which is a 2D manifold, in 2D manifolds you have uniformization theorem or Riemann mapping theorem. Okay, you have the Riemann mapping theorem is a well-known one for Riemannian manifolds, but you have an analog for Lorentzian manifold also. And in particular, one of the consequences of this is that every single 2D Lorentzian manifold is conformally flat. Okay? And you can identify it with a subset of R11 via this conformal flat mapping. Okay, and this has turned out to be very useful for understanding the structure of the boundary of space-time. Based on the asymptotics that we have, that I showed you earlier, in the case where there's no fiber collapse, the case that I care about, the base manifold Q maps to R11, maps to the Minkowski space in the conformal flat picture. In both of the fiber collapse cases, Q does not map to the entirety of R11. It maps only to the case where T is positive time half of Minkowski space. So there is a sort of in some ways you can think about these as saying that the singularity is reachable in finite conformal time. Not infinite time, but infinite conformal time. Whereas in my case, the singularity is not reachable in finite conformal time. Now this is significant because the mechanism for instability is what is always going to be a nonlinear reinforcement of perturbations, that you're going to have a self-interaction between certain things in your PDE that gets bigger and bigger and bigger. And for this to grow to infinity, it's going to take time. If you have a finite conformal time, you do not have enough time for the nonlinearity to build up and generate singularity. But if you have infinite conformal time, my idea is that you actually have enough time for this to happen, and this can actually generate an instability. Okay, so now let's talk very quickly about the instability in the last few minutes. So the mechanism we'll be using is shock formation. So non-gravitating compressible fluids on a flat background is going to form shocks in 1, 2, and 3 spatial dimensions, and not in 4 and higher. It's interesting. This is for different reasons. But in 1D, this is originally due to Riemann, and then much later due to Peter Lex in the 60s and Fritz John in the 70s. They analyzed this sort of in great detail. In 2 and 3 dimension, the work actually only was completed in the 1999 through 2008-ish. Okay, this is due to Sergei Alinak and Dmitry Christodoulou. And the key idea is this notion of genuine nonlinearity, which is basically just saying that your fluid variables will have a self-reinforcing nonlinear self-interaction that makes perturbation gets bigger and bigger and bigger as time goes along. Sort of one of the mechanisms that you show up in 1D, which is something that you learn in first class in PTEs, is the method of characteristics, also known as the method of Riemann invariance. In this situation, you get automatic absolute value bound for the fluid variables because you have invariance. Riemann invariants are invariant by definition, and if it's invariant, it stays the same for all time, and so you have bound on size. The shock is coming from the first derivative of the invariant, which are no longer a invariant. And the spatial derivatives solve some sort of transport equation of Riccati type. So, and they blow up in finite time, and this is sort of well studied in the basic example of the Burger's equation. But what I want to mention here is again that initial derivative of size epsilon requires time 1 over epsilon for the blow to occur. Okay, so the smaller the perturbation, the longer you have to wait for the shock to form. Okay. Now, in our result, we're not going to define, as I said before, that what Big Bang should be outside of cosmological ansatz, but what we do have is that we know for the cosmological Big Bang solutions, we know that the limit at the singularity of the density should be plus infinity, while the spatial derivative is going to be 0, right, because it's spatially homogeneous. What we're going to prove is that we have shock type behavior for perturbations, which means that at a new singularity for a perturbed solution, rho is going to remain bounded on a singular boundary, and the blow up is entirely of the spatial derivative of rho. So it's entirely opposite kind of blow up behavior. Okay, and so this tells us that the solution, that the perturbation provides an instability, provides a different kind of behavior compared to the Big Bang behavior. Okay, let's see. Yeah, okay, so let me just skip the top part and talk about the bottom part. So the reason that this actually works in our setting, so you think that, okay, I talked about earlier how for epsilon size initial data, you have to wait 1 over epsilon time for things to blow up. But now, if you go back to our initial ansatz for the cosmological Big Bang solutions, we proposed that the Big Bang solution terminates at the Big Bang within finite time. So how do I get enough time for these shocks to develop? And for this to understand this, we have to go back to what it means to form a shock. Shock wave is formed by intersection of acoustic characteristics. What does that mean? That means that you have, due to the nonlinear effects in the density of your say air, let's say, certain wave packets of sound will move faster than other wave packets. And if you have one faster moving wave packet catching up to a slower moving one, this is what happens when you have shock waves. Okay, so the idea now is that, hey, in Big Bang, we not only just have finite time singularity, we also have a spatial collapse. It's part of our assumption. So the spatial distance is shrinking. And so it's easier for the wave packets moving fast to catch up to the previous one if the distance between them is also getting smaller. And so if, in order to actually, for this to happen, we have to study what is the ratio between the rates of spatial collapse and the rates of temporal collapse. And this is precisely the thing detected by the Penrose diagram earlier. And the fact that my Penrose diagram has infinite conformal time tells us that I have an infinity of conformal time for me to wait for this catch-up to happen, and we can actually prove that this is indeed the case. Okay, so I don't want to say this. Yeah, okay. So so here's a schematic statement of the main theorem. It's as theorems for an SPDE goes. This is sort of par for how complicated it looks. We're going to start out with a given cosmological Big Bang solution. We're going to fix some time, some reference time for the initial data, R1. So R1 is just going to be where I prescribe my perturbation. Okay. For any R star between the Big Bang time and the time where I prescribe the perturbation, I can find epsilon and delta positive such that three things hold. First, if the initial data at R1, the perturbation, is almost homogeneous in that it differs from homogeneous less than epsilon, then the only possible singularity between R star and R1, R star being the time that I prescribe here, has to be a shock. It cannot be another kind of blow up. Now, if additionally the data satisfy a quote-unquote largeness assumption, that at one particular point, you have large derivative of the unknown, so bigger than some delta, then there in fact is a singularity between R star and R1. So combining these two, this tells you that when there is going to be a singularity, that is of shock type. Okay? And finally, the part that actually gives us instability is that if you take R star, the reference time where the singularity that we want happens, we take it down towards R0, we can also take delta towards 0. And this tells us that we can find arbitrarily small perturbations that generate a shock. But the shock time is going to be coming closer and closer to the Big Bang time, R0. So this is sort of a structure that's very common nowadays in sort of studying of the stability results, where you reduce the stability result to the instability result. You reduce the instability result to a partial stability result combined with a guarantee of singularity formation. Okay, I think I'm just going to leave that at that. If you want to talk about it later, I can answer questions about it. Okay, let's see how I'm doing on time. I can talk a little bit about about one technical thing, because this is kind of interesting. So one of the hardest part about this is to prove that rho, the density of the fluid, remain bounded. So the basic, before in the Riemann invariance case, it's an invariant alone characteristic and therefore it's automatically bounded. But now, since we're having coupling to gravity, the space-time geometry involves also, so they're going to feed back into the equation for rho and c, and this might lead to rho becoming bigger and bigger and bigger. So we can write down a characteristic equation for rho and c, and it turns out to have some right-hand side. It depends on a bunch of things. It depends on rho itself, c itself, the metric itself, and also the first derivative of the metric. This is where the connection comes in. Okay? This is where the gravitational effect manifests. Now, there's two things happening. First, there is a driving force to bring rho to infinity, and we know that rho is going to go to infinity at the Big Bang boundary because that's what we found in the ODE case, and that is coming from rho, c, and GQ. But there's also going to be additional gravitational feedback in the inhomogeneous case, coming from the fact that all of a sudden, once we start perturbing, the spatial derivative of the metric is going to be non-zero. And that's a part that's going to be hard to control. That's one of the main technical difficulties in the argument. So to control that, the only thing that we can do is just look at the equation for GQ. Now, GQ has two components. It has three equations. The transport equation looks like a derivative of GQ equal to something depending on rho, c, and GQ itself. Two of them are evolutionary. This is partial r of GQ equals something. And one of them is a constraint equation, which gives you something about the partial s. So this is the part where constraint equation is very nice, because with the constraint equation, it gives you a free L infinity bound, the elliptic equation. You get some basically elliptic estimates that you can use to control one factor of one component of the GQ spatial derivative. For the other one, you have to take a S derivative of the equation and look at the corresponding equations. But the problem now is that if you take one derivative of the equation, you're going to have a nonlinearity that depends on the derivative of rho and derivative of C, which we're expecting to form a shock with expanding these two components to go to infinity. So how do we handle this potential infinity in our argument? And this is an idea going back to 1 John in the 70s and 80s, which basically takes advantage of the fact that the sound waves are propagating at non-zero velocity. So if you're doing this sort of integration process, you are doing a sort of a transfer. It's sort of let me just summarize in one word. You're taking advantage of some sort of transversality, okay, which allows you to gain some additional regularity compared to the non-transverse version of the estimates. Okay, and the actual implementation actually is very technical, so I'm not going to mention that too much. All right, good. So let's just very quickly talk about a sort of few things about the result. First, one of the issues of geometric PDEs is that you always have to fix a gauge, and this is sort of even an issue at a naive level, that if you solve, if you want to prove a stability result, and you're proving it on a manifold, if you choose a very bad diffeomorphism between your initial thing and your perturbed thing, then the diffeomorphism with respect to that particular diffeomorphism, what may be stable may appear to be unstable because you chose a really bad diffeomorphism. So choosing a diffeomorphism is important in helping you correctly prove stability and instability in a geometric PDE. What we did using the RS coordinate system, the orthogonal coordinate system, is that we chose a Eulerian coordinate system in fluid language. A big question is whether you can choose the Lagrangian coordinates, because the Lagrangian coordinates is known to actually improve regularity for fluids, but we have not been able to get it to work. So this is a sort of possible future direction. I'll skip the next point. That's not that important. Another thing that's interesting is that our theorem only applies when Q is assumed to be non-compact. When Q is spatially compact, something weird happens, and we could not quite figure out why. And this is a result my student found. That I asked him to think about the compact case, and he showed that if I decouple the fluid from the gravity and study this on compact manifold, then there's actually a class of solutions which is stable under perturbations with no shock formation. And we do not quite fully understand. I mean, we know why it is true from the proof, but we don't know why physically this is there. So this is something that is also worth thinking about. But the thing is that, because of this, it's possible that that shock formation is actually non-generic in a spatially compact case. I'm not quite sure what the correct expectation is. And finally, sort of in terms of the physical interpretation of our result does not tell you that Big Bang doesn't happen. That's not what it is. It just says that a particular type of Big Bang is non-generic. So you should think about this as saying that in the actual physical setting, the kind of Big Bang that you should expect to see is not this kind, but the FLRW or the Kastner type Big Bangs. Because otherwise, you'll be unstable to perturbations. And in fact, we actually conjecture that in the other two cases, FLW and Kastner cases, even with the highly nonlinear matter model with the compressible fluids, these should be dynamically stable. But this is something that we're going to leave for future work. All right, I think that's it. Thank you all.
between considering fluid at Big Bang and airs at Big Bang
And what Big Bang?
and hot air?
Oh, hot air.
and fluid.
Yeah.
What is the big difference?
So actually okay. So the question was about what is the difference between hot air and fluid. So air is a fluid. So we should think about in this previous situation, hot air is just a hot fluid, and I'm not really caring about temperature since I threw away entropy as part. So yeah, so the title is basically just saying that we're looking at perturbations where in the fluid case in air, because it's compressible, and we change a little bit of we blow on it, so it has a little bit of a wind or ripple, which generates singularity.
So the difference between them is I can blow the air, but I cannot blow the fluid. Is that?
No. You can blow the fluid. So the air, you should think that air is a type of fluid. In fact, I use air in the title for the following reason, that the result concerns compressible fluids. Okay, so there are two types of fluids you should study: the compressible and the incompressible. Air is compressible. We can make dry ice and things like that just by compressing it down to a very small area, sort of volume. Water, on the other hand, is very incompressible. It's very hard to compress water. So I use air to emphasize the fact that we're studying compressible fluid.
Thanks. The second question is, why we assume at least one dimension spatial collapse at the beginning?
Oh, that's just because sort of how we have an intuitive idea of what a Big Bang looks like. The Big Bang, we think about what's happening as things starting at a point or a collapsed state that explodes, right? So if we think about that as the picture of what Big Bang is, at least one dimension should be I mean, this is sort of a very weak assumption. Sort of like one way to think about it is just saying, hey, I am going to assume my singularity in some sense has a Hausdorff dimension at least one fewer than the generic spatial slice. So things are sort of collapsed.
Is there any possibility that the collapsed dimension is the time dimension but not spatial?
That is so. If you look at what's happening there, in all three cases that I mentioned for asymptotics, the time dimension is automatically collapsed. So in fact, that's kind of that comes in almost as part of the requirement.
Any other questions? So if there's no further questions, let's thank the speakers again for his wonderful talk.